this case, KSP is given, but you need to calculate solubility in presence of a common ion, which is coming from MgBr2. So, at the beginning, when you add MgF2 in MgBr2, you already have this much Mg in the solution. And X is the additional quantity because of the breakdown of these MgF2. So let's now find out. Again, X is the solubility. Now in this new solution. So I can now write down this new expression. KSP will be given by Mg2 plus times F minus squared. And I'm getting rid of this solid from the bottom. So now you'd have here you have Mg2 plus concentration is 1.0 times 10 to the negative 2 plus X. That we're getting from here. Times F minus. F minus concentration is 2X. That's a squared. Now in solving this problem, obviously this is the solubility. If X is small, you can ignore this. Then you can solve it, and KSP value is given 4.0 times 10 to the negative 12. Then you need to solve for X, and that's solubility. For a quick solution, you can initially ignore X, and then it would not be a quadratic equation anymore. So you can just solve for X and make sure X is 5% smaller than this number. Otherwise, you'll have to do this problem by quadratic method. So once you solve for X, you get the solubility value. Now the next problem is on buffer capacity. Just a few minutes ago we talked about buffer capacity. High buffer capacity means you can add more acid, but still it would hold its pH. So for that high buffer capacity, you need a higher concentration of weak acid and its conjugate base, or weak base and its conjugate acid. So I already mentioned about that, so hopefully that will work. But let me give you a simple example with few numbers. HA, weak acid, and A minus. And let's put down some numbers. 0.100 molar, and this is 0.200, this is 0.300, and 0.500. This is 0.200, and this is 0.300. If I give you three solutions, these are all buffer solutions. This is conjugate acid, this is conjugate base, and that makes a buffer solution. But which of these three solutions, this is solution 1, solution 2, solution 3. Which one of these three would have the highest buffer capacity? Answer would be this, because that has the largest concentration of HA concentration as well as A minus. In other words, that's going to last longer when you're adding acid or a base. So this is a pretty qualitative question that you can quickly get an answer, primarily by looking at the values. Now something I want you to make sure that you understand this. If I have a strong acid and weak acid, or very weak acid and relatively stronger acid, how would I know them from Ka values? Let me just write down a simple expression. HA giving H plus A minus. Say this is a very weak acid. What that means is a very small part of this would break down into H plus and A minus. On the other hand, if it's a relatively stronger acid, a lot more of this HA would break down, and you get a lot more H plus and A minus. How is it going to influence Ka value? This is how you write down Ka. H plus times A minus divided by HA. For a stronger acid, you'd have a larger concentration of H plus and A minus. So you'd expect a larger value. For a weaker acid, you get a smaller value. So make sure you understand that. What about pKa? pK is minus log of Ka. So larger Ka would have a smaller pKa. So that's why in organic textbooks, if you find a smaller pKa value, that means you're talking about a stronger acid. Then there will be common sense. One of the questions can come from your common sense. And I'll explain to you what kind of question that would be. Like you need to know lemon juice, that's acidic, pH less than 7. Vinegar, is that acidic, basic, or neutral? You should know that it's acidic. Vinegar has acidic acid. Milk, saliva, they're slightly acidic. Human blood, slightly basic. Seawater, slightly basic. Household bleach, they are strongly basic most of the time. So you would expect one question like that. That would come from your common understanding of this type of substances. Then titration curve. And I'll give you one such graph to you. Titration curve. And we often call pH titration. So you'd have, say, pH and ml of sodium hydroxide. I'll just show you one example. Say I have something like this, and we have all these. This is the end point. So that's 7. Let's assume that you have 7. So you have 4, 5, 6, 7, 8. Okay, so you did a titration like this, and your pH titration curve looks like this. This is the end point. The end point pH is 7. Question is, this is a strong base. What kind of acid you'd have there so that your end point pH is equal to 7? So in order to explain that to you, let's look at some of these concepts. When you add strong acid and strong base, what to expect. Example of a strong acid is HCl. A strong base is a sodium hydroxide. So we're giving you here giving you a strong base during this titration. We're adding a strong base. What are the products? Sodium chloride plus H2O. Now the question is, when they combine together, we get a salt. This is a salt of a strong acid and strong base. We can always split this compound into 2 halves. The acidic part and basic part. Sodium is the basic part. Even if you don't know anything, but if you just know the product, sodium is coming from sodium hydroxide. Cl is coming from HCl. Always a salt you should be able to split into acidic part and basic part. Now what kind of base is this? A strong base. Group 1A and 2A hydroxide. What kind of acid is this? A strong acid. So if that is the case, if you got a salt of a strong acid and strong base at the end, which one is going to be dominant? Neither. So this should be neutral. And pH equals to 7. So if I get pH equal to 7, right away I can say this is a strong acid, a strong base titration. So since this is already a strong base, unknown acid has to be a strong acid. So this is acid-base titration. I should write down here, acid-base titration. Now let's discuss other cases. Instead of a strong acid, strong base, say I have weak acid plus a strong base. Weak acid could be HA, acidic acid. A strong base could be sodium hydroxide. Product would be NaA plus H2O. Well, what kind of salt is this? Salt of a strong base and weak acid. Which one is going to be dominant? Just by looking at it, you know it has to be the basic, because you have a strong base, NaOH and HA. A strong base, weak acid. So this should be basic. And pH for basic would be greater than 7. So if you have something like this, you'd have greater than 7. What about the third case? I have a strong acid plus weak base. In that case, salt would have more acidic strength. So it would be acidic. That means pH at the equivalence point would be less than 7. Okay, so make sure you learn by looking at the titration curve what kind of acid you'd have in order to have pH at equivalence point equal to 7, less than 7, or more than 7. This concludes my second review session on chapter 16 and 17.